Hello everyone, I'm back with another heat mass video. Today is going to be about the concept between evaporation. So for the video, I have my notes blank. I just have written what our agenda is today. So the first thing we're going to do is learn about what the driving force is behind evaporation. So we're specifically going to look at a container. It's just going to be water in there, and then we're going to pass nitrogen gas over top of this water and see how the water will eventually evaporate into vapor mix with the nitrogen gas, and the nitrogen gas will have some sort of concentration gradient that drives downward into the water, and kind of just explain the driving force behind this evaporation and what happens with the nitrogen gas and the water when it turns into vapor. And then the second part is going to be actually determining the molar flux of the water. So how, what the flux is of that certain situation, that example. Excuse me, I'm sorry. When we have specific boundaries set, so like the length and other things like that, being able to actually plug in the numbers and solve and see a numerical value. So the first thing I'm going to do is draw what our example looks like. So like I said, we're going to be looking at a container that's going to have liquid water in it. And then over the very top of the container, I'm just going to draw this thin boundary layer. It's not necessarily a real layer, but it's going to show the difference between pure nitrogen gas, which is being passed over top, versus where the nitrogen and the water is starting to mix. So this is what I have here. We have our liquid nitrogen on the bottom. That in-between layer is where the nitrogen gas and the now water as a vapor is starting to mix due to evaporation. So as that liquid water starts to evaporate and turn into vapor, it's going to mix with the nitrogen gas. And then at the very top, that's just our pure nitrogen gas that we're passing over top of this container, which is the driving force for evaporation due to the nitrogen gas. So this is going to be our specific example. I'm going to go ahead and denote the interface between the water, the liquid water, versus the nitrogen, hydrogen is going to be our interface there. So I'm going to denote that as 0. That's kind of our starting position. That's what we're really looking at here. And then at the very top, when it goes from the mixed nitrogen water mixture into just nitrogen, that's going to be our final length. So I'm going to denote that as L. So I've just kind of set our system here, the direction that we're looking at. So upwards is going to be the positive direction. And then, in order to analyze this problem, we have to look at an equation that we used in our past, one of our past videos. So when we're talking about mass transfer, with heat transfer we have Fourier's law, but with mass transfer we have Fick's law. So as we recall, Fick's law is going to be J equals negative C d dx over dz. So I'm sure that was just a bunch of numbers to you, or sorry, a bunch of letters to you. So that's the equation that we have for Fick's law. So we can recall that the big J stands for molar flux. So this is how the moles of whatever we're looking at is changing due to some sort of concentration gradient. So as we recall, the C is going to be concentration. So that's like how many moles we have. And then the D is going to be our diffusion coefficient. So this is due to whatever material we're looking at. That will change depending on that. And then the dz, or sorry, the dx over dz, that is our change in position of the system. And then we can also recall that we have that negative symbol because, like with Fourier's law, heat would go from areas of higher energy or higher temperature to areas of lower energy or lower temperature, and that's kind of the natural flow that it would diffuse. So it is the same with this mass flux here. So this is going to be due to high to low flow. All right, so I wrote a bunch of things down, so I'll let you look at this for a second. So I just labeled each of these variables depending on what they mean. So we have our molar flux, concentration, the negative is due to the high to low flow of energy, our diffusion coefficient, and then the change in position of the system as we go through. So that's why we have the 0 to L labeled there, is because that's where we're looking at our change in position. That's where that kind of comes into play. So a couple of important things to note about this specific example before we continue. First of all, this is going to be at steady state. So that means there are no components changing due to time. Everything is going to remain constant. So any sort of velocity associated with it, anything like that, is going to be null to change due to time. Secondly, we also have no pressure gradient in this example. So because this is an open system, technically all we have is like this thin little boundary layer here that's not actually truly a boundary. It's not an enclosed, this is not enclosed. There is no pressure difference between where this nitrogen is and where this nitrogen water mix is. There's no pressure difference. So there's going to be no pressure gradient, which means that there will be no driving force due to pressure. So any sort of evaporation that this system is experiencing is solely due to the molar concentration, due to a concentration gradient rather than a pressure gradient. So that is very important to note too. And then, as I said, the driving force for evaporation is due to concentration changes. So there is a concentration gradient. And now we're going to kind of look at what the concentration gradient looks like. So if we recall from chemistry, we have the PV equals nRT equation, and when we're talking about concentration, we're talking about some sort of molar moles depending on how much volume we have. So our concentration is going to be in units of moles per liter. So we're looking at how much concentration, how many moles we have in a certain liter, a certain volume. And then we have our PV equals nRT here. And if we want to solve for concentration using this equation, we can recall that V is volume, obviously, and then N is going to be number of moles. So we can rearrange this equation in order to be moles per liter, aka N over V, which is going to be equal to P over RT. So we just divided by the volume, and now we have the moles over liter, or N over V, equals P over RT. P is our pressure, R is going to be our gas constant, and T will be our temperature. And this is kind of easier for us to analyze the concentration because we can look at measurable pressure of whatever we're looking at. Gas constant remains the same, and then a measurable temperature as well. So this makes it a lot easier for us to analyze our concentration. And we can also recall that in order to find our concentration, which in Fick's law, the C stands for total concentration of the entire system. And since we're looking at the entire system, this is going to be a mix of the nitrogen and the hydrogen. So if we kind of break that down a little bit, we can see that the concentration for water plus the concentration of the nitrogen. So these are the two components of our system. The concentration of the pure H2O and the pure N2 is going to be equal to our total concentration that we have in this system. So I've just written here that C in our Fick's law equation is equal to the total concentration of the system, which is equal to our two individual components added together. So now, since we can look at the concentration of our individual components, our pure H2O and our pure N2, the pure H2O is going to be at, our X equaling 0, and then the N2, actually, we're not going to denote that yet because that just makes it a little more confusing for no reason. We're going to plot what the concentrations kind of look like, the concentration gradient, as we move from position 0 to position L for each of these. So this is going to give us a better idea how our concentration is going to change for these two as we go from 0, which is where this interface is, all the way up to L when it becomes pure nitrogen. So let's go ahead and draw our graph here. And we're looking at our change in position. So this will be X here, going from position 0 to position L. And then we're looking at how this concentration is going to change, which is once again moles per liter. So this is the graph that I have here. If we're looking at H2O, water, here we know that the water concentration here is going to be its highest. It's going to be the highest it could possibly be because this is our pure water here. And then when we start to diffuse away from the water, the concentration is going to get lower and lower because we're getting farther away from our pure concentration of water. So if we were to draw that, we can show that at position 0, our concentration will be very high for water and become very low. So this is what I have here. And then if we're looking at our N2, we can see that here the concentration of nitrogen is going to be pretty low, if not 0 here, because this is where our interface is. The nitrogen has not fully diffused down yet because we have our pure nitrogen up here, and the farther you get away from it, the less nitrogen you're going to have. So we can mark that at position L, our nitrogen is going to be at its highest that it could be because that's our pure nitrogen once again. And then as we get, excuse me, sorry, my nose is itchy. As we get farther down towards position 0, which is where that interface is, it's going to be much lower. So this is kind of what that relationship looks like. So as we can see, these have inverse relationships. So the closer we are to having a higher concentration of water, the smaller our concentration of nitrogen is probably going to be. So this means that they're going to have inverse concentration gradients. So as our water goes up, the concentration gradient will get smaller. And as our nitrogen goes up, as our nitrogen goes down, the concentration is going to get smaller there too. So they have inverse concentration gradients. So what this means is that as the H2O is starting to evaporate and the molar flux is going in the upwards direction, so the concentration gradient is going up, our N2 is going to diffuse down because they're going opposite directions. One issue we have with this is that the H2O can go up all at once because it's just going into the atmosphere. There's infinite space there for it to diffuse into. For the N2, it's a different situation because it'll be going down into our pool of liquid water, but it can't do that because it's liquid or it's vapor, and the H2O is liquid. So the nitrogen gas has nowhere to go because it's going to hit into that water and have no space to go to, and it can't just crowd up there. There's no room. So an issue that we have with the way that we've set up the problem right now, it can't be this straightforward because that suggests that the N2 can just diffuse down, but there's liquid water here stopping it from doing that. So this is not possible. So since this is not straightforward in being that, oh, we can just say that these molar or these concentrations are going to be opposite of each other because the nitrogen has nowhere to go, we can now rewrite this equation to look at the total flux. So J is our molar flux, and if we want to look at the total flux of the system, we can say that total flux is equal to our molar flux plus whatever mole fraction we have of what unit we're looking at times the total flux. So that's this equation here. So we're saying that the total, I'm going to write 1 here because that will help. So we have the total flux of our unit 1 plus the mole fraction of unit 1, which is what you can find through this equation, plus, well, the total flux is equal to the mole flux plus the molar fraction, so however many moles of this entire system we have, that is unit 1, times the total flux is going to equal the flux of just that one component. So if we put this in terms of nitrogen, because we know that nitrogen can't have a molar flux going down. It's not possible. It has nowhere to go. So we know that the total flux of nitrogen, so total flux N of N2, has to be 0 because it can't have that total flux going down. It can't be diffusing down because it has nowhere to go. So if we want to solve for this after having this revelation and still prove the fact that there is some sort of balancing flux, so since the total flux of the H2O is going upwards and the N2 is not going downwards, it's not going upwards too. It has to remain where it is because otherwise there's not going to be any sort of driving force for the H2O to evaporate. If the H2O is going up, the N2 must remain here. It must stay in its spot. And if it has that flux pushing against it from the H2O, it has to have some sort of driving force down, not enough to actually go down, but enough to sustain where it is, position-wise. So there is some sort of flux happening with N2, it's just not happening in the same way that it is with the H2O. So we know that the total flux of N2 is going to be equal to 0, but that is also equal to the molar flux of N2 plus YN2, which is the amount of moles of N2 that we have in the system, times the total flux. Excuse me. So this is what I have here. The total flux of N2 is going to equal 0, which is also equal to our molar flux of N2 plus the mole fraction of N2 times the total flux. And as we recall, like I did similarly with the concentrations, the NT, or the total flux, is going to be equal to the flux of the nitrogen plus the flux of the H2O. But we just said that the flux of the nitrogen, the total flux, is going to be equal to 0. So that just means that our total flux in the system is only going to be equal to the flux of the H2O. So we can substitute here that 0 equals the molar flux of N2 plus YN2, or the mole fraction of N2, times NH2O, which is equivalent to the total N. So this is our simplified equation at the bottom here. We have 0 equals mole flux of N2 plus the mole fraction of N2 times the total flux of water, H2O, because that is equal to the total mole flux, or the total flux, sorry. Okay, so now that we have this equation, which is also JN2 equals negative YN2 NH2O. So I just rewrite that to be the molar flux equals, instead of just 0 equals. Excuse me. Now that we have this equation, which is showing our driving force for evaporation when we have the normal flux going from the H2O coming up, we're showing the kind of counteractive molar flux that we have from N2 to counteract the driving force of the H2O coming up. Now we can look at our specific example with actual values and solve for the molar flux while having specific values. So I'm going to flip over to the next page and redraw our example, actually giving us some numerical values this time. We still have our H2O, H2O-N2 mixture, and then at the very top, our N2 being passed through. So this time we're going to know the length of the H2O-N2 mixture, which is going to be equal to 1 meter. So, yeah, I just redrew our system. This time we know that it's 1 meter long. We are going to know that our diffusion coefficient from Fick's law. So I'm going to rewrite Fick's law really quick. So that's going to be J equals negative CD dx over dz. We're going to know that d is going to be equal to 10 to the negative fifth meters squared per second. So that's going to be our diffusion coefficient, 10 to the negative fifth. And then we're also going to know our pressure will be 1 bar. And we're going to go ahead and convert these into SI units so that we can use the gas constant in SI units, which is typically what you'll find it in. So it's just easier to convert all of these units over to that. So 1 bar is equal to 1.03 times 10 to the times 10 to the fifth pascals. And then our temperature will be 50 degrees C, which is also equal to, we'll put this in kelvins, which is going to be 323 kelvins. So you just do 50 plus 273, that'll be 323 Kelvin. So these are some values that we're going to have defined for this problem. And now we can go ahead and take the equation kind of that we derived for N2, but we're first going to look at H2O. So we started over here by saying that our total flux can be equal to the molar flux plus the mole fraction times the total flux. So we're going to write the same situation for our H2O now. We know that the flux of our H2O can be equal to the molar flux of our H2O, which is found through Fick's law, plus the mole fraction of H2O, so however many moles we have of H2O at the certain position, times the total flux of the system. So now we have our equation written for H2O, and we're going to go ahead and plug some of these things in. So we have JH2O from Fick's law. We just have to plug in the H2O values here, and then we can also figure out the total flux, because we know that N total was equal to NH2O plus NN2. Okay, so now that we have this equation, we can start plugging things in. So we can write that NH2O is equal to, now we can plug in Fick's law for the molar flux, negative CD. And you might have been thinking, what is the dx over dz? So what is the x? So we know that z, this is the concentration due to change in position, but concentration of what? We're looking at concentration of the moles. So x and y are both ways to show molar concentrations. They're just used differently. They're just used differently depending on whether you're looking at a vapor or a liquid. So y is typically used if you're looking at a liquid, and then x is for vapor. So we can actually write this as dyH2O, because H2O is represented by the molar fraction with a y. So we can substitute that in there, and then dz remains the same because z is talking about what position we're at. Plus yH2O, and then we can also recall that we found in this instance that the flux of N2 was equal to 0. So our total flux is just equal to the flux of H2O. So after we substitute all of these things in here, we have that negative CD, change in the molar concentration of H2O over change in position, plus molar concentration times total flux, which is just equal to NH2O once again. And then we can also recall that earlier in the video, I said that our concentration is equal to moles over liters, which is also equal to N over V, which equals to pressure over gas constant times temperature. So I've just rewritten that here. Concentration is the same as, or is in units of moles over liter, which is N over V. So that's just what I had written over here, again, written here now. So we can plug this in for this concentration once again. And we happen to know our pressure because the pressure is not going to change depending on where we are in the system. There is no pressure gradient. And then we know our gas constant because that remains constant. Actually, sorry, the pressure is not going to equal this 1 bar because that's our atmospheric pressure, and we're looking at the pressure in our H2O, in our liquid. And this is actually going to be a known value. Like you can just Google this wherever. Because we're just looking at normal H2O under normal conditions, we can just Google what this pressure is. And then gas constant, we do know, temperature as well. If you happen to not know your pressure, though, there's different ways that you can find it using different equations. So you can use Antoine's equation or Clausius-Clapeyron equation to solve for that. But because this is a pretty normal circumstance, we can just Google that and find what that number is. So, since we can just look this up, we can see that the pressure of water, liquid water, at 323 Kelvin is going to equal 12 times 10 to the third pascals. So that's just something that we Googled, super easy to look up. But if we couldn't look something up, or we are not supposed to, or some situation where you can't just easily look it up, then you can use the Antoine or Clausius-Clapeyron equation to solve for that. So, since we know the pressure of H2O, we can actually solve for the pressure of N2 as well. So the pressure that we were given for this example, it's essentially 1 times 10 to the 5th pascals. I'm just going to write that as 1 instead of 1.013, which is what it technically is, but it's close enough, so we're just going to round it to make it a little bit easier on ourselves, is equal to our total pressure. And once again, we're going to use the way of solving by saying that the total pressure is equal to the pressures of each component added together. So total pressure is equal to the pressure of the H2O plus the pressure of the N2. So since we know the total pressure is going to be equal to the pressure of H2O, which we just found, 12 times 10 to the third PA, we can solve for the pressure of N2 because we know the total pressure and the pressure of H2O. So you can just see here, I've written, now we can solve for N2, and that pressure is going to equal 88 times 10 to the third pascals. So that's just good to have on hand for later. Okay, so now we can come back to our main equation. NH2O equals, we'll plug in what we found for concentration. So negative P over RT for our concentration now, and then we have our D still. And then when you write the coefficient of diffusion, which is that uppercase D, since we're looking at H2O and N2, we're just going to write it from 1 to 2. So D1, 2, evaluating component 1 to component 2, aka from water to N2. That's just typical denotation there. And then times the dy H2O over dz plus YH2O times NH2O. So this is our equation after we plugged in for our concentration, and we're gonna reorganize this a little bit to get the NH2Os on the same side, and then we're gonna move the dz over to this side too, and move, or sorry, not yet. We're actually just gonna move the NH2O over first, and pull that out, so that we would have NH2O times 1 minus YH2O. So we have NH2O on the left side. We're going to subtract YH2O times NH2O and then factor that out to get NH2O times 1 minus YH2O. And then our right side will remain the same, otherwise negative P RT D12 DYH2O over DZ. So this is what we have now, kind of simplified it a little bit. Now we're going to move the dz over to the left side of the equation and the 1 minus y h2 over H2O to the right side of the equation. And we're doing this because we want this YH2O to be with this YH2O so that we can take the integral. And then you have to have the dz on this side and evaluate on that side in order to take the integral of both sides. So now we have NH2O dz equals negative P RT D12 times, and then we'll have 1 over 1 minus YH2O because you got to divide that, times DYH2O. So this is what we have now. We moved that DZ over and then divided the 1 minus YH2O, still have the DYH2O. And now we're going to take the integral of both sides. Okay, so now that we're taking this integral, we're going to have to find what the boundaries are for these. I've written my integrals in here. So this is going to be a constant because it's not evaluated based on change in position. It'll be a constant flow no matter what position you are at in the system. And then these are all constant too in regards to the mole fraction. So we need to find the boundaries for this. And since we're just looking from this here, we've already set it as being 1 meter. And we had denoted from this example that 0 was the interface and whatever the length was the top part. So we know that the boundaries for the left side of the equation will be from 0 to 1 meter dz equals. Then we have our right side of the equation with our constants out front. And now we need to find the corresponding concentration, and we're looking at water once again, the corresponding concentration of water at position 0, because it has to match up the boundaries, both sides of the equation. So if we're looking at the concentration of our water here, we had found that our pressure here is equal to 12 times 10 to the third. And then if we want to find the corresponding pressure mole fraction, we can recall that we say, I actually don't see it written here. We can recall that we say that, oh wait, it is here, sorry. The total pressure is equal to the pressure H2O plus the pressure N2. And so this, the pressure ratio between the total pressure that we have with the pressure of the H2O on top. So pressure of H2O divided by our total pressure will be equal to our mole fraction, is what I'm getting at here. So I said that really awkwardly. But it's like when we recall that the total, or the flux of H2O is equal to the mole fraction of H2O times the total flux. It's the same kind of thing with our pressures here. So we have that our total pressure will be equal to the mole flux of, the mole fraction of H2O times, I'm sorry, I keep writing this backwards. The pressure of H2O, so the partial pressure of H2O is equal to the mole fraction of H2O times the total pressure. Excuse me. So in order to find the total pressure, or in order to find the mole fraction, we have the pressure of the H2O divided by the total pressure. So this is how we find our boundary. I'm so sorry, that was really roundabout. Kind of scatterbrained today. So YH2O will be equal to the pressure of H2O at that position, which is 12 times 10 to the third, divided by the total pressure we found to be 1 times 10 to the fifth. So we can find the mole fraction of H2O as being 0.12. So that will be our boundary for the bottom one. And then when we get to 1 meter, we said that that mole fraction of water was essentially 0. So we'll equate that boundary as being 0. And then we have 1 over 1 minus y H2O times dy H2O. So I had solved over here for our mole fraction of H2O by equating the partial pressure of H2O is equal to the mole fraction times the total pressure, and then solve to get 0.12. And now we have our boundaries for both sides, and we'll just take the integral. So integral of 1, so the left side will be NH2O times 1, so NH2O essentially, equals negative PD12 is constant times RT. And then when you take the integral of 1 over something, it's just equal to the natural log. So we have natural log of 1 minus y H2O evaluated from 0.12 to 0. So this is what we have here. This becomes just 1, and then we have here, so then we can go ahead and solve for this side. Okay, so now we can factor in this negative that's in our constant into the natural log, flip it around a little bit, so we have NH2O. That 1 is just 1, it can be taken away. PD12, no more negative there because we're going to add it to our natural log. So that'll flip around the 1 minus to be y H2O minus 1. Still evaluated from 0.12 to 0. We plug that in, and H2O equals PD12 RT. And that'll become natural log of 1 divided by 0.88. So this is what we have here. We just moved that negative in here and then evaluated it 1 over 0.88. And we know the values for all of these, so we can just plug everything in here. So we have NH2O is equal to 1 times 10 to the 5th. That was our total pressure that we had found, times D, which was 10 to the negative 5th, over RT, 8.314 is our R. Our temperature is 323. Natural log of 1 divided by 0.88. And I know that these units are going to work because we have already converted everything to SI. If we had not, then there would be a slight issue here. We'd have to write out all of our units, make sure they all are correct. But because we took the step to make sure that they were correct along the way, I know that these are the correct values and we're going to have correct matching units. So when you do this, you get 4.76 times 10 to the negative 5th. And that is going to be in joules per meter squared per second. Sorry, moles per meter squared per second. And that is going to be our answer for what the flux is, what the molar flux is of the water if we're looking at this problem with these certain boundaries. So this is the complete answer we have here, and we have derived that whole thing on this page, and then this was how we derived how the water evaporates and what happens to the nitrogen with the water evaporating upwards. How does the nitrogen counteract that? And that's going to be it for my video today.